Hey y'all, let's now talk about how we control microbial growth. Because sometimes you just don't want microbes growing where you're doing surgery. You just don't want microbes growing where you're making food. You just don't want microbes growing some places. So there's a bunch of terminology here. Sterilization means you have removed all microbes. That includes endospores. If you remember endospores, those super resistant, hard to kill structures that some bacteria can make. This is really important to sterilize endospores, to remove endospores, because one type of endospore, Clostridium botulinum, can cause a food poisoning known as botulism. In botulism, all of your muscles will go into a flaccid paralysis, which isn't a great way to survive. So we want to get rid of these endospores so that we don't kill people. Disinfection is a treatment on an inanimate object, so something that's not living, to kill or inhibit growth of microbes. So when you come into lab, you start the day by spraying your table down with alcohol, wiping it down. That's disinfection. Antisepsis is a chemical method, so not a physical method. This is a chemical method to disinfect the skin or the mucous membranes. So when you go get a vaccine, your skin is wiped off with alcohol or some sort of antiseptic treatment before getting the vaccine. When you put hand sanitizer on your hands, that's antiseptic. Or even if you're gargling with a chemical to disinfect your mucous membranes, that's antisepsis. Degerming is a mechanical removal. So, something like wiping off the table with a wet rag after you've sat at the table and ate your food. You are physically picking up some of those microbes with the wet rag. That's degerming. You're washing your hands. You're not necessarily killing the bacteria on there, but you're physically pushing those things off of your skin. Sanitation is when you remove microbes from eating utensils and food prep areas. So washing the dishes, that's sanitation. Degerming, let's skip that term again. Sepsis and asepsis, these are terms we're comfortable with from lab. Asepsis means there's not significant contamination. Sepsis means there is microbial contamination. So aseptic technique, that technique that allows you to avoid contamination, which is important in surgery. It's important in labs. Then a lot of words. I've already used some words this semester that end with one of these suffixes, but these two suffixes are very important. This suffix "cide" means to kill. So suicide, homicide, these mean to kill. Biocide kills living things. Germicide kills germs. Insecticide kills insects. A viricide, a fungicide, a bactericide. Static means it stops it or it steadies it. So bacteriostasis means you have not killed that bacteria, but you have stopped it from growing. So alcohol is a good biocide. Refrigeration is bacteriostatic. Okay, so flaming your loop is bactericidal. It will kill the bacteria, but throwing it in the freezer is bacteriostatic. It'll stop it from growing, but it's not dead. The rate that microbes grow is also going to be a logarithmic curve, opposite from what you see at a growth curve. And that microbial death rate just refers to the rate that your microbes are dying at it. How well your treatment is going to kill your bacteria will depend on some different qualities. One is the microbial characteristics. Is your bacteria gram-positive or gram-negative? Does it have a capsid? Does it have a endospore? The environment. What type of organic matter is there? What's the temperature? Is there a biofilm? The time of exposure. So if you remember in lab when we went through our safety rules the first day, If we have something spill on the table, you need to douse it with alcohol and leave it sitting there for 5 minutes because it takes time to clean it up. And the number of microbes. If you're trying to kill 1 microbe, it's going to be a lot faster than if you're trying to kill 2 billion microbes. Okay, so how is it possible that a solution that contains 1 million bacteria would take longer to sterilize than a solution that has 500,000 bacteria? Okay, then let's talk about some different ways that a microbial control agent can act on a cell. One is by damaging the cell wall and the cell membrane. This could include damaging the lipids in the phospholipid membrane, protein channels. This is going to result in the contents of the cell leaking out. If the cell is leaking and losing all of its contents, it's going to stop growing. One is by damaging proteins and enzymes. This often uses heat or chemicals that can just break hydrogen bonds. And this is going to allow that cell to stop making the things it needs to grow, so it stops growing. And damaging nucleic acids. This could involve heat, this could involve radiation, this could involve chemicals. This is lethal to a cell. Without your DNA or your RNA, you cannot replicate, you cannot create proteins, you cannot do any sort of metabolism. You can't do anything. It is goodbye to that cell. Okay, so now your question. Would a chemical microbial agent that affects plasma membranes affect humans? Why or why not? Some different physical ways we can control microbes. One is by using moist heat. By and large, moist heat is going to denature proteins. This could involve boiling. This could involve using an autoclave. An autoclave is basically a giant instant pot. It has steam under pressure, very high temperatures, very high pressure. Autoclaves are used to sterilize media, instruments, syringes, solutions. We use them in our lab. If you'd like to see them, I'm happy to show you our autoclave sometime. Autoclaves are used in a lot of surgical settings to sterilize, syringes and materials that you need to reuse. Dry heat is going to be mostly oxidative. This would be things like flaming your loop, putting things in an oven. Desiccation is just the removal of water. Desiccation tends to be more static than cidal. Osmotic pressure, using a lot of salt and sugars. This is very popular to preserve food because it tastes really good. Leads to plasmolysis of the cell or the death of the cell. And then high pressure. That increased pressure will just kind of force those proteins and carbohydrates to just close in on themselves. It alters their three-dimensional shapes, so they're no longer functional. Low temperature is also able to be used to control the growth of microbes, but it's going to be bacteriostatic. It's not bactericidal. It'll stop it from growing. It won't kill it, though. This would include refrigeration, deep freezing, and lyophilization, or freeze drying. We talked about these in Chapter 6, so that should be very fresh on your mind. Feel free to go back and review that if you'd like to. Radiation and microwaves. These are also physical methods. Ionizing radiation, non-ionizing radiation. This should be things like X-rays, UV rays. They damage DNA. I'm not going to ask you a lot of detail about this, but if you can tell me X-rays, gamma rays, UV rays, damage DNA. Microwaves. Oh, it seems like every Thanksgiving there is some trend about cooking your turkey in a microwave, right? Super not a cool thing to do. Microwaves produce a little bit of heat that can kill, but they're not antimicrobial. So, if your loved one decides that TikTok trend is for real and tries to do it, do not eat their little microwave turkey because it's not antimicrobial. Okay, how is microbial growth in canned foods prevented? Go back and review. I told you a few times in Chapter 6 and in Chapter 7. So make sure you're comfortable with that. I'm going to finish off this chapter in our next video. Feels like this one's gone long enough. So I'll meet you back to talk about disk diffusion, one of my favorite things we do in lab. And I'll see you later. Bye.